Hey everybody, happy Thursday. I hope the quiz went well. Again, the plan for today is to review for the Chapter 7 exam. The Chapter 7 exam is not on Monday, it is on Wednesday. And the material that we're going over on Monday is not on the exam. So it's just over the stuff that I'm going to talk about, review through today. A reminder that I have posted the solutions to the review problems for the Chapter 7 exam. So you can feel free to work through those problems. I would recommend that you try working the problems on your own before looking at the solutions. And especially, not for the hyperbolic ones, but for all the other integral problems. The best way to do those problems first is to figure out what integration technique you would use. And I'll talk back through that today. But you need to be able to make that mental list of all 6 techniques that we've had for integrating and think through that list and say, what are my best options? And basically you can narrow down to, I only have 1 or 2 options, and that tells you what direction to move. So you're not just kind of staring at a particular integral, okay? So before we do integration technique, let's just go back and look at, again, section 510 real quick. So this is on hyperbolic trig functions. So hyperbolic trig functions. This is sinh x and cosh x. And you should remember, for these functions, you should remember their definitions. Okay, so sinh, I'll go ahead and write it again, is e to the x minus e to the negative x over 2. Cosh is e to the x plus e to the minus x over 2. So you should remember those definitions. I can ask you for those. Second thing you should remember is what the graphs of these look like. Okay. Sinh, just as a reminder, kind of looks like, it's a little bit like x cubed, but it involves exponential, so it's not quite like x cubed. Cosh x is a little bit like x squared plus 1. It looks something like that. You remember that cosh is actually an example of the type of way that a wire hangs on a telephone wire. So anything that you hold up that hangs, that dips like that is actually a cosh function. All right, and finally, you should remember the derivatives of these functions. Okay, the derivative of sinh is cosh, and the derivative of cosh is sinh. And you can actually get that from the definition just by differentiating those e to the x functions. So the derivative of sinh is cosh, and the derivative of cosh is sinh. So these are really nice functions in that you don't have to worry about co-functions. When you differentiate them, you get a negative. None of that shows up there. All right? Okay. So those are the things you would need to remember from the hyperbolic trig function category. Now let's do our Chapter 7 stuff with integration techniques. Okay, so we're going to have the technique, what to look for, and then what to do. Okay, the technique, what to look for, and then what to do. So the first thing we had, again, was simplifying. And simplifying is a fairly broad category. We had things like multiply out, divide, move things around so they're in a better form. Like if we've got 1 over x squared, we make it x to the minus 2, so we've got a power function, that kind of thing. So I won't list all that stuff out here, but this is stuff that we've seen before. Then we had substitution. We actually had substitution back in Chapter 5. But again, the thing that we look for is either a composition or something in the integral is the derivative of something else. So we look for the du that's the derivative of something. And then what we do there is we let u equal the inner function. And again, substitution is usually one of our first go-to things that we try, because if substitution works, it's usually a good thing. Our next technique was integration by parts. And integration by parts was the reverse of the product rule. So here we're looking for products. But we had a few tricky things that could come up. So we could have 1 times a function. We could have to do this multiple times. And we could have that case where you do integration by parts twice and you get back to the original integral, but with a minus sign or something, and so you get integral equals some stuff minus the integral, and you can bring that over to the other side and get that 2 of the integrals equal this stuff. And that actually lets you solve for the integral. We call that circular reasoning. And in this case, with integration by parts, you let u equal one thing and dv equal the other, and then we've got that formula that we use. Integration by parts, for the most part, is the last thing that we try. We usually don't like doing integration by parts, but sometimes you have to. Okay, next thing that we looked at was integrals involving trig functions, so we call these trig integrals. And so we looked for trig functions here. Usually these trig functions are grouped in collections, so we see sine and cosine grouped together, tangent secant grouped together, cotangent cosecant grouped together. And we looked at certain patterns in these, but really what we were doing in all of these trig integrals is we were using these other techniques along with some formulas. So we had the formula sine squared plus cosine squared is 1, right? Tangent squared plus 1 is secant squared. Cotangent squared plus 1 is cosecant squared. And then in the case where we had even powers of sine and even powers of cosine, we had these half-angle formulas of 1 minus cosine 2x and 1/2 times 1 plus cosine of 2x. Okay? Basically, we used those formulas along with some of our, along with these other techniques to try to get to a place where we had a simpler integral. So if you remember, for instance, we would have, like if I had the integral of sine cubed, one of the questions that I asked myself was, is there a du in there? So if I pulled out one sine, sine is the derivative of what? Well, it's the derivative of cosine. So then I think to myself, is there a way to change those other two sines into cosines? And that's where that formula comes in. Sine squared is 1 minus cosine squared. And so now you would be at a place where you do a substitution. Okay? So that's the kind of thing that came up there. But you can only do that when you have trig integrals. Now we looked at sine and cosine combinations, and another day I looked at tangent secant combinations, and I mentioned that cotangent cosecant combinations act a lot like tangent secant combinations. And then when all else fails, if things are really weird, you switch everything back to sine and cosine and then just move forward from there. Right? Okay, the next thing that we looked at were trig substitutions. And that we do this in 3 special cases. Typically when you see square roots, not always, but typically, and you see one of 3 square roots, 1 minus x squared, 1 plus x squared, or x squared minus 1. And in each of these cases, you do a substitution. So in the first case, I would let x equal sine theta. The second one, I'd let x equal tangent theta. And the third one, I'd let x equal secant theta. Now, if this is not 1, if it's something else, like 9 or 4 or 16, then you have to think through, what do I need to add on the front of this so that that number can actually appear in both places and I can pull it out, right? So for example, if I had 9 minus x squared, I would put a 3 here, so that 3 squared would give me a 9 here and a 9 here, and I can pull that 9 out of the square root to become a 3, and I would be left with 1 minus sine squared. And 1 minus sine squared is cosine squared, square root of cosine squared is cosine. So the point of this technique is that doing the substitution makes the square root much simpler. The one thing to remember with this is that in order to substitute back for x's at the very end of the problem, we would have to draw our triangle and figure out what's the sine, what's the cosine, etc. Okay? All right. And then the last integration technique that we had was partial fractions. And again, what we look for there is a polynomial over a polynomial. And there's a 4-step process to what we do here. So we do long division if the degree of the top is bigger than or equal to the degree of the bottom. That doesn't often happen. I probably won't give you an example of that because it gets pretty complicated. The next thing that we do is we factor the bottom. Then the longer part of this is we find the partial fraction decomposition, the PFD. And that was where we take each of the terms and we write it out individually with numbers, with coefficients like a over x minus 1, b over x, c over x squared, that kind of thing. And then we solve for those coefficients. We've done some examples of those kinds of problems now. And then the last technique here is that we integrate. So we fall back on some of these previous techniques to be able to do these problems, okay? This list is a great, I want to emphasize this a lot. This list is a great list to keep in front of you or to keep in the back of your mind as you're doing these review problems. Because you need to go down this list and check off, here are the things that'll work, here are the things that won't work for a particular example problem. Because if you can narrow these down to 1 or 2 possible techniques, or even just one, then that's the only direction that you can go, and you have to go that direction. So then that prompts you to move forward. The other thing to remember is that most of these techniques only lead you to an easier integral. So you eventually have to get to the place where you get to an integral that you can do. So you have to feel comfortable with those integration formulas as well. So this is it for the review. You've got a bunch of problems there. The best thing for you to do is just practice starting those problems and figuring out what integration technique do I start with. So you'll have time in class here to work on that. If you've got the previous homework assignment that didn't get done, you can work on that and finish that. The solutions for these review problems are there on RenWeb. Mrs. Barabo also has them, so you can take a look at those. All right? So I'll be praying for your studies. I know you've got a lot of stuff going on, I'm sure. And I hope you guys have a great weekend. And let me know if you have any questions, if anything comes up. Take care.